All right, let's try some problems here. Let's take a look here. Let's do number 2. Consider a sample of ideal gas initially in a volume V at a temperature T and a pressure P. Does the entropy of the system increase, decrease, or stay the same in the following processes? A, the gas expands isothermally. The entropy increase, decrease, or stay the same? The gas expands isothermally. Entropy increases. Do you guys remember isothermal versus adiabatic? What's the difference between isothermal, expansion, contraction, and adiabatic, expansion, contraction?
Adiabatic is constant pressure.
Adiabatic is not constant pressure. Adiabatic is something different. One of the things I used to do, this is, I told you about, I think, the student next to me in thermodynamics. One of the things he did was he did all the homework problems in the book, and I thought, that's impossible. You can't do all the problems. Well, it is impossible. You can't do all the problems unless you have the complete solutions manual. If you have the complete solutions manual, which they did, at UCLA, they give you the complete solutions guide. I was used to having the partial solutions guide. For Petrucci, we have the complete solutions manual. You can do every single problem. You don't really do it. What you do is you read the problem and then you read the solution. Why? A lot of people say don't do that, but you're beginners. If you're beginners, the more problems you see, the better. If you're a beginner at this, you don't want to limit yourself. I can do these 4 problems and that's it. And you give me a 5th problem that's outside the scope of the 4, then I can't do it. No, that's not the way you want to do it. When you're a beginner, you want to do as many problems as possible. And so I know they say, well, in order to do as many problems as possible, you can't waste too much time on one single problem. If you're spending 1 hour, 2 hours, 3 hours on one single problem, that's a complete waste of time. It's a complete waste of time because you're like, okay, I got to learn the entire forest, but I'm going to just spend all my time studying this one little weed that's growing next to the tree here. And I'm just going to whittle away months studying this one weed. By the end of 3 months, what have you learned about the forest? You can probably tell me everything about that one little weed, but you can't tell me much about the forest. And so here, what we're going to do is we've got to look at a lot of problems. One of the things you can do for rapid review, this is what I call rapid review. When you do a rapid review of Chapter 7, you have the complete solutions manual. You have every single homework problem. Just read the problem, read the answer. And that'll get you started refreshing your memory on Chapter 7. What are you going to do? You're going to look at one problem in Chapter 7 and then that's it? That's not effective review. All right, so you'd review something like this. This is Chapter 7. In an adiabatic process, the system is thermally insulated. There is no exchange of heat between the system and the surroundings. So adiabatic means heat is not exchanged. It's a closed system, but it's an insulated closed system. The way we think about it, the way we visualize it, is it's a closed system, and if we're thinking in terms of constant pressure, it's a closed system like this, but now what we have to do is we're going to visualize our closed system, which has a movable lid. It can move up and down. Normally we can exchange heat and work with the surroundings, right? This would be a closed system with a movable lid that the volume can expand and contract. But in this case, we're going to super insulate this, thermally insulated, like this. So heat is no longer exchanged. So if we heavily insulate this container, then the heat is going to be retained here, not exchanged. And the only thing we can exchange with the surroundings would be work. And so, this is back in chapter 7. So here, for the adiabatic expansion of an ideal gas, A, does the gas do work? If we did an adiabatic expansion of an ideal gas, adiabatic expansion is, okay, this lid moves up, the gas expands. Was work done? Yes. Okay, work is done. Does the internal energy of the gas increase, decrease, or remain constant? So does the total energy increase, decrease, or remain constant? This is adiabatic. This is the system. So if it's adiabatic, okay, so we expanded the lid of the container. So now the volume is bigger. And so the lid rose up. Work was done, for sure. Who did the work, the system or the surroundings? The system did work. And so if the system does work, does the system lose energy, gain energy, or stay the same? It loses energy. So the total energy went down, internal energy. And ideal gases, the only energy term is the temperature, so the temperature has to go down.
Well, where does the heat from the work go?
There's no heat. There's no heat exchange. And so what happens is, if the system loses energy, its temperature must go down. And so where did the decrease in kinetic energy go? That went into the work of expanding the volume.
Yeah, but my question is, where does that go in the system?
No, okay. What you're saying is that heat can neither be created nor destroyed? Is that what you're saying?
Well, no. Energy can't be created.
Energy cannot be created nor destroyed. So the heat went into, where did that heat go? The heat went into doing work. That's where the heat went. Does that make sense?
The whole system loses energy still.
What's that?
Well, the system loses energy still.
The system, no, okay. Oh, I see what you're saying. You're saying that the energy of the system, okay, in a way, the system lost energy. In a way, it gained energy, right? Or no? In other words, actually, let's see. We'll do this. Energy is neither created nor destroyed. And so if we start off, let's start off with this volume. This is the volume here. This is the temperature. We'll say this is at 25 degrees C. And so this is our initial volume. And so the energy is here. The energy is going to depend on having it at 25 degrees C here. And then what we do is we're going to increase the volume. If we increase the volume, then we have to do work. Work is going to be done, right? And so when we think about the total energy here, the total energy here, U initial, and then the total energy here, U final. Well, what is the final, U final? And so if the volume expands, what's going to happen? Well, the system's got to do work. If the system does work, then the system's going to lose energy or gain energy. It's going to lose energy, but where did that energy come from? If the system loses energy, where did the energy come from, or where does it go?
Well, we'll go to the surrounding.
Well, here the potential energy is 0 plus
Kinetic energy.
the kinetic energy. And so in this case, if the system loses energy, then it's going to have to do some work. It loses energy, and therefore U final is going to be down here. U final is down here, but what happened? Well, the system lost energy because it lost energy in expanding its volume, so now the temperature is going to be less than 25 degrees C here. And so where did that heat, the heat wasn't transferred because this is adiabatic, so the heat is not transferred. How was that heat lost though? Well, the temperature went down, heat was lost. Heat was lost into doing work and expanding the volume. But energy cannot be created nor destroyed, so it seems like something's missing here.
Does it turn into potential energy?
No, it doesn't turn into potential energy because this is ideal gas. Ideal gases have zero potential energy. And so where did the work go? Or where did the energy go? No, not entropy. Okay, what happens is this. If the system does the work, then energy is conserved, so that means the surroundings must right. What happens is if the system does the work, the system's energy decreases, the surroundings energy is going to increase. And so the surroundings, that's where that energy went. And so the surroundings is going to be it, but the system's temperature is going to go down. This is for adiabatic. For isothermal, if we do the exact same thing, it's a lot easier to visualize because if this is isothermal, what's going to happen is this. The system's volume expands isothermally, so that means we end up at the same temperature. If we end up at the same temperature here, isothermal means the same temperature, then where did the energy come from to expand the volume? Where did the energy come from? The system had to do work, but the system didn't lose any energy. And so where did the energy come from to expand its volume? The surroundings. What happens is this is going to cool down, but the surroundings will warm up the system back to 25 degrees C. So the system gains the energy from the surroundings in doing that work. And so this is something you guys should review, this chapter 7 stuff. This is first law of thermodynamics. When you go back to the homework here, first law of thermodynamics in chapter 7. For example, here, 59. Do you think the following observation is in any way possible? An ideal gas is expanded isothermally and is observed to do twice as much work as the heat absorbed from its surroundings. Explain your answer. Is that possible? Number 59. An ideal gas is expanded isothermally and is observed to do twice as much work as the heat absorbed from its surroundings. Possible? Impossible. That would be a violation of the first law of thermodynamics. Energy is neither created nor destroyed. We'd have to create energy if the system were to do twice as much work as the heat absorbed from the surroundings. And anyway, this obviously this stuff is confusing. This is why you have to go back through it over and over again to make sure it's clear in your mind. Otherwise, if you're struggling with this, the chapter 7 stuff, then what's going to happen as you continue on. You're always going to be on shaky ground. You're never really going to understand anything. So what you have to do, and this is what I had to do, I had to go back to the beginning and make sure I understood everything from step 1, because if I didn't understand something here, then that's going to screw up my understanding of things as things get more advanced. And it's really going to limit you as far as your understanding of this. And so conceptually you have to go back, and what you do is you go back through all these, Do you think the following observation is in any way possible? A gas absorbs heat from its surroundings while being compressed. Is that possible? Can a gas absorb heat from the surroundings while being compressed? And so, impossible. For the system, which is the gas, to be compressed, it's got to lose energy. it can't absorb energy, and if it absorbs, this is not possible. This would be another violation of the first law of thermodynamics. First law of thermodynamics says this: the delta U is equal to Q and W. You know, energy is going to be conserved, and it's going to be exchanged with the surroundings in the form of heat and or work. So we have to understand this. And so go back through chapter 7, make sure. I mean, conceptually, it's very confusing stuff, but we need that. For chapter 13. You know, not totally everything, but some stuff. You know, chapter 13 is just a continuation of chapter 7. And so we're continuing chapter 7. Consider a sample of ideal gas initially in a volume V at a temperature T and a pressure P. Does the entropy of the system increase, decrease, or stay the same in the following process? The gas expands isothermally, so we think, okay, what stays the same? When a gas expands isothermally, right, isothermal expansion, the gas does work, but the temperature stays the same. It's an ideal gas, therefore its energy stayed the same. The initial energy and the final energy, that means it had to absorb heat from the surroundings, otherwise it can't stay the same, maintain the same energy. Well, gas expands isothermally. What's going to happen to the entropy? The entropy is going to increase. Well, we don't really need to know isothermal. We just need to know expand. Gas expands, it's got a bigger volume. Positional entropy is going to be much greater because here you have it in a tighter volume, and so there are fewer positions that the gas can adopt. If you expand the volume, there are more positions. If you double the volume, they're going to double the entropy because there's going to be twice as many positions that the gas can occupy. The pressure is increased at constant temperature. The pressure is increased at constant temperature. So we increase the pressure, and so that means the system volume contracts. If the system volume contracts, the surroundings volume had to increase. If the surroundings volume increases, that means the surroundings does the work, the surroundings loses the energy, and the system gains the energy. And so when the system volume contracts, then the energy should increase, the temperature should increase, right? But it's at constant temperature. And so these types of things we got to think, but right now we don't. You know, right now we can ignore this. We can just think in terms of this. The pressure is increased at constant temperature. Well, there are different ways to increase the pressure. You know, one way is you can introduce more gas particles in there. You know, constant temperature, you can introduce more gas particles in there. Another way is you can just decrease the volume, etc. The gas is heated at constant pressure. Okay, so these are the types of things that we have to think about. But as far as entropy goes, then it's just going to be a matter of this. Bigger volume here, the gas is heated, higher temperature, etc. And so what you probably should do is go back to chapter 7 and do a little bit of review. But it turns out it's not going to be this complicated to answer the questions I wanted to cover right now. And the questions that I want to cover right now are this. The questions I want to cover right now are driving force, qualitatively. What's happening to energy here? So we're going from a liquid to gas. Is the potential energy going up, going down? In other words, what's happening with the energy? Is it increasing or decreasing if we go from liquid to gas? It's increasing. Energy is increasing. What's happening to entropy? Entropy is also increasing. So is this going to happen spontaneously or not? Well, that would be a question mark, because on the one hand, energy is saying no driving force, but entropy is saying driving force. So we have conflicting driving forces here. And so this one's a question mark. Let's go to B. What's happening with the energy here? What do you think is happening with the energy? So we're going from copper sulfate trihydrate, then adding 2 gaseous water molecules to form copper sulfate 5-hydrate or pentahydrate. And so we're incorporating 2. What do you think is happening with the energy? The energy is decreasing. Energy, whenever we form intermolecular attractions or whenever we form bonds, bond formation or intermolecular attraction formation releases energy. Breaking bonds and breaking intermolecular forces absorb energy. And so energy is decreasing. What's happening to entropy? Entropy is also decreasing. And so we have different, our Chem 1A driving force says the first one, no reaction. The first one's no reaction because energy is increasing. But can we just say that there's no reaction? No, we can't say that because of entropy. Entropy is saying yes. And so it's becoming more complicated. The second one, in Chem 1A, we'd say for sure there's going to be a reaction here because we're going from higher energy to lower energy. And the driving force is going to more stable products. Well, this is a more stable product, but we can't say for sure because we're losing entropy. And so there's a conflict there. If we go to the third one, let's see here. What do you think? SO3 and hydrogen to SO2 and water. Can you tell me, is energy increasing or decreasing?
Staying the same.
How did you get it staying the same?
Because two moles of any gas at the same temperature have the same kinetic energy.
Okay, you're thinking in terms of ideal gas now. I'm not thinking in terms of ideal gas anymore. I'm thinking in terms of real gases. Real gases are going to have chemical properties. When I look at the chemical properties, what type of reaction is this? Is this a metathesis, the ion combination? Is it an acid base? It's a redox reaction. And automatically I can see this energy is going down. How can I tell? How can I tell that energy is going down? Because of this. Hydrogen is a pretty decent oxidizer or reducer. It's actually both. It can go either way. It can be an oxidizer or a reducer. But normally when we think about hydrogen gas, it's a reducer. And so I think about this, I'm going from a stronger reducer. What's a reducer over here? Are there any powerful reducers here? When we look at the oxidation states here, this +6, so sulfur trioxide is my oxidizer because sulfur is going from +6 to +4. And then hydrogen is my reducer. Now, when I go over here, I look, okay, then if sulfur trioxide is my oxidizer, sulfur dioxide must be the conjugate reducer. So this is my reducer. And then I compare hydrogen versus sulfur dioxide. Which one do you think is a more powerful reducer? And oxidizer, what do you think is a more powerful oxidizer? Sulfur trioxide or water? Sulfur trioxide. This is going from stronger oxidizer reducer to weaker. That means we're going down in energy. So energy is going down. What's happening with entropy? Entropy is staying about the same because we got gases here. So the entropy, not much is happening. So energy is going down. Entropy is about the same. This reaction should go. This reaction is going to have driving force. There's no conflict there. Energy is going to be the dominant term. This reaction is going to happen. D. This is not balanced, but you can kind of get the idea. What type of reaction is this? This is a redox reaction too. And I see a very common oxidizer. The common oxidizer is O2. Right? O2 is a strong oxidizer. Now, when I look at this, we have H2S. H2S turns out to be a pretty decent reducer. But over here, is water a strong oxidizer or a strong reducer? No, water is extremely weak. I already know that this is going to be stronger to weaker because I see it. Water is both a weak oxidizer and reducer. In this case, what is water? Well, what's happening here is oxygen's being reduced, that is gaining electrons, is -2, that's 0, and sulfur is losing. And so we go from -2 here to +4 here. And so that means the oxidizer is going to be sulfur dioxide versus oxygen. And for the reducers, it's going to be H2S versus H2O. H2S is going to be a much better reducer in this case. And SO2 should be a better oxidizer than SO2. And so this reaction energetically should go. Now it's not balanced. We've got to balance this to see, because we need to balance this to see if we're going to have a reaction or not. And so let's take a look at if we can balance this by our standard method. Maybe. Let's try it. We got 2 hydrogens, 2 hydrogens, 1 sulfur, 1 sulfur. And then we look at the oxygens over here. We have 2 plus 1, it gives us 3 oxygens over here. We only have 2 oxygens here, so if we multiply by 3 halves here, we're good. And so we didn't have to go to skeleton redox for this one. Skeleton redox is at the end of chapter 5, but this one we could just balance outright. And this is going to be H2S plus 3 halves O2 gas. Now this is always tricky because in redox there could be other things in here which can screw you up. And so we have to make sure that the oxidation states are balanced. Whenever we balance it by just changing the coefficients in a redox, we can't do that. We can't do that because what happens is the oxidation states might not balance. And so an example of that would be something like this. Actually, let's not do that. I'll do an example later, but the way we do this to make sure everything's properly balanced is we'd have to look at the oxidation states to make sure that everything worked out properly. And so we do it atom by atom. So we have 2 hydrogens at +1. And then we got a sulfur at -2. And then we have 3 halves in O2, which is 3 halves in O2 would be 3 oxygens at 0. And then here we have a hydrogen at +1 and 2 oxygens at -2. And then we have a sulfur at +4 and then 2 oxygens at -2.
Just one oxygen.
Oops. 2 hydrogens, 1 oxygen. Okay, there we go. And so did anything happen to the hydrogens? No, nothing happened to the hydrogens. They stayed the same. What happened to the sulfur? The sulfur went from -2 to +4. How many electrons did it lose? -6 electrons. So 6 electrons were lost by the sulfur. And then the oxygens, we have 3 oxygens at 0 going to 3 oxygens at -2. And so if we go from 3 oxygens at 0 to 3 oxygens at -2, how many total electrons were gained? +6. And so when we balance a redox like this by changing the coefficients, we have to be careful. We have to make sure the oxidation state's also balanced. That is, the number of electrons lost is equal to the number of electrons gained. Sometimes that doesn't happen. When you atom balance a redox, sometimes the electrons don't balance. There are 2 ways of balancing redox. This is called the oxidation state method. In Chem 4, they had two sections. You can balance by oxidation state, or you can balance by half reactions. The other way I would have balanced this is by splitting it up into half reactions. H2S goes to SO2, the other half reaction would be O2 goes to H2O. And then I balance it here, and then combine them. This is in chapter 5. And so this way you will definitely get it right. This way, a lot of people try to shortcut it and get it wrong because the oxidation states won't balance. But anyway, let's see what's happening with the entropy. As far as the entropy goes, it depends on how many moles of gas we have. And so over on the left, we have 3 halves, which is 1.5, and we have 1. So altogether, we have 2.5 moles of gas total on the left. On the right, we have 2 moles of gas. So if we're going from 2.5 moles of gas to 2 moles of gas, what's happening with the entropy? Entropy is going to go down. And so the more moles of gas, the higher the entropy. In other words, if we're looking at this, this is about, you know what the volume of a mole of gas is at a 25 degrees C in 1 atmosphere? Roughly? 22 is at 0 degrees C. At 25 degrees C, it's closer to 24 point, no, not 0.2, 24.5. 24.5 or 25. So this is about 25 liters. This is about, so this is going to be 50, this is going to be about 62, 63 liters. And so this is 63 liters going to 50 liters. So we got 63 liters going to 50 liters. 63 liters of gas is going to have a higher entropy. And so what's happening with the entropy is going down. And so we got two things going on here. The entropy is going down and the energy is going down. And so the energy goes down, that's reaction, spontaneous. The entropy goes down, that's non-spontaneous, that's no reaction. So one says reaction, the other says no reaction. This is a question mark. This one we don't know. You know, if we just use the Chem 1A, what I just covered with chemical reactions, we'd say a reaction occurs here because we're going from stronger to weaker. You know, but that's not always the case because we have to worry about what's happening with the entropy. So now, what we got to do is, if we got to worry about what's happening with the entropy, then we have to figure out how to quantitate the entropy. You know, we want to put numbers on these things. We want to put numbers on the energy. We can put numbers on the energy. It's easy to calculate the energy for this. You know, we're doing it qualitatively, but we could do this quantitatively using thermodynamics. In thermodynamics, what's the easiest way to calculate what's happening with the energy? Now, most of the chemical reactions we do it under constant pressure or constant volume conditions? Most reactions that we do. Constant pressure. And so if we do things under constant pressure, then we got to worry because the system can expand or contract. We're doing it in a closed system. If the system expands or contracts, then it screws things up because there's energy exchange now between the system and the surroundings in the form of work. And that plays with your head with the numbers because it doesn't add up, right? If we're looking at the system alone, then it's easy. You know, if we're looking at the system alone, the system loses energy, the system loses energy. But now we got the surroundings, and the surroundings, you know, the system, let's say the system loses 10 joules, $10. Well, the surroundings can come in and give $10 to the system, right? To make up for that loss. And so when we're dealing with the system and the surroundings, this is why we have to add the PV state. You know, H is the total energy, but now we got to see what's happening with the surroundings. In order to see what's happening with the surroundings, we need to know the volume of the system. If we know the volume of the system, we can see what the volume of the system is doing because the volume of the system is going to impact the volume of the surrounding. And so this term is going to help us understand how the system interacts. Whereas if we just look at an internal energy, we could care less what happens with the surroundings because internal energy is just the energy of the system with no interaction with the surroundings. And so we need this PV state here when we're dealing with enthalpy. Well, we're doing this. We're doing this under constant pressure. And so we always, when we're doing things under constant pressure, we got to worry about what's going on with the surroundings, you know? And therefore, we got to do this using delta U or delta H. This reaction we want to do, if this reaction is under constant pressure, do we want to do a delta U calculation or a delta H calculation? Delta H. We do a delta H calculation. Sometimes delta H and delta U are about the same thing. You know, one is a delta U and a delta H going to be about the same. Actually, let's take a look. Here. Is delta U and delta H about the same for this? Reaction A. No. No, which one's bigger, delta U or delta H? Which one's bigger? Delta U or delta H? which one's bigger here is delta U. Delta U is going to be bigger because, or no, actually delta U is not bigger. Delta H is bigger. Do you know why delta H is bigger? Because if we do this in a bomb, then we don't have to worry about the volume. If we do delta U is what we use in a bomb. We go from a liquid to a gas. No volume change. System volume stays the same. If we do this with a delta H under constant pressure, then what happens is the liquid occupies much smaller volume than the gas. And so the volume has to expand. And so we're going from a very small volume, the milliliters, to 25 liters roughly per mole. As the volume expands. As the volume expands, then we have to add more energy to do the work of expansion against the surroundings. Now, the intention here is not to basically what you want to do is you want to review Chapter 7. I've mentioned this so many times already, but how? To what level do you need to understand Chapter 7? Well, you need to be able to understand it to this level where we can talk about these kinds of things. This is a totally one-sided conversation. Well, not completely, but, it can be, to a lot. It'd be one-sided because, what is that? What is he talking about? What's all this stuff? Do I need to know this? Do I need to know this for the test? Well, unfortunately, that's what happened to me. I was supposed to know all this stuff for the test when I transferred to UCLA, but I didn't. And so you have a chance to, if you're continuing on in wherever and energy is important, you have a chance to review this stuff so you can understand it a lot better. And so I'm going through a whole bunch of this stuff, not in the intention of reviewing it, but for the intention of showing you what you're supposed to be able to, what you're supposed to know from Chem 1A. Right. Now, whenever we have a question mark, what do we do? There's a question mark here. Who's going to win? Is the energy going to win or the entropy going to win? Well, to calculate the energy is easy. Okay, if we're doing this under constant pressure, then the delta H, what's the easiest way of determining delta H for this reaction? What's the easiest way of figuring out the energy change quantitatively for this reaction? Well, tell me all the ways you can determine delta H. How do we determine delta H experimentally? H final minus H initial is impossible, unfortunately. This is not totally impossible. It's impossible to do it with any accuracy. And so this is never done. Why is it never done? H final minus H initial is never done. The reason is because H final is equal to U final plus PV final. U final is equal to the potential energy plus the kinetic energy plus PV final. All these things you're supposed to, this is the problem with thermodynamics. Thermodynamics, you're supposed to know all these relationships to come up with all the equations, et cetera, and know how things interrelate. But the only way to know that is to really grind through it over and over, not the night before the exam, but well before the exam, so you can put it all together mentally with all your neurons connecting here. And the problem is not this. These are easy. Volume final's easy. Pressure, easy. It's constant. Kinetic energy, that's easy. What's the temperature? The problem is the potential energy. What is the problem? In Chapter 7, they mention the problem with potential energy. Potential energy is not something that's easily determined. Why?
Many different forms.
So many different forms. You know, the problem is what is the absolute zero potential energy? And so what you can do is you can take a molecule and you break all the bonds. And you go, okay, there's potential energy stored in the bonds. You know, you form bonds, you release energy, you break bonds. It costs you energy, and that energy is the potential energy in the bond. And so there's potential energy stored in the bonds. But is that it? No, there's potential energy stored in electrons. Electrons are held in the nucleus. So to remove the electrons is going to cost you energy. Ionization energy 1, ionization energy 2. We add them all up. You know, all the way, however many electrons it has, we can determine that. That's no big deal either. The problem is there potential energy in the nucleus? Yeah, okay, so you break apart all the protons, all the neutrons, and all the, what else is in the nucleus? Oh, that's it, right? Just protons and neutrons. So we break up all the protons and neutrons as nuclear energy, and then that's it. But is there any potential energy in the proton? Can we break the proton up into smaller pieces? And the answer is, do you know? Yes. The people are looking for the decomposition, the spontaneous decomposition of proton. And it turns out that protons can be broken up into smaller pieces, right? So where does it end? What's the absolute zero when we've broken everything apart and then we can put everything back together? Is that something that's easily calculated? No, but it's also not fair. Some people say, hey, that's not fair because in chemical reactions, do we ever mess with the nucleus? You don't mess with the nucleus in chemical reactions. And so you say, okay, well, if we ignore the nucleus, then can we do it still? And it turns out, no. And so people calculate this potential energy, but the error that's associated in that calculation from quantum mechanics. Quantum mechanics, you know, the Schrodinger equation is very difficult to solve, and the Schrodinger equation can only be solved exactly for the hydrogen atom. Anything more complicated than hydrogen, you have to use approximation methods. When you use approximation methods, then you're going to introduce error. And the error associated with these calculations is bigger than the delta H itself. And so these calculations are kind of worthless, and nobody does this. In fact, how do people do this then? Well, let me just tell you, people do this experimentally using calorimetry. You know, they calculate Q, the reaction, divided by the amount. And so delta H is just Q, the reaction over the amount of reaction that they had. You could do that experimentally, but do you want to do calorimetry for determining delta H? No. There's easier ways.
I was going to ask about Hess's law.
Yeah, you want to do Hess's law, but Hess's law, adding up equations, there's a special version of Hess's law where you don't have to add up the individual equations because we always use the same type of equation. If you only use one type of equation, then they automatically cancel out. If you use Hess's law with different kinds of equations, then you have to add up the equations, you know, so that these cancel, those cancel. But if we only use one type of reaction, one type of equation, then we can do a very simplified version of Hess's law using what type of reactions? We can use a very simplified version of Hess's law using formation reactions. Formation reactions are the easiest, so if we do this, we can use this equation. The easiest way of determining delta H is if we have the formation, the standard enthalpies of formation, we can just do mu P, standard enthalpy of formation for the products minus the sum of mu R, so the standard enthalpy of formation of the reactants. This is the easiest, and then this data we just get from Appendix D, so we don't have to do any kind of experiment. And so this is an easy calculation from Chapter 7. And so we can figure out the energy. You know, if it's negative, if delta H is less than 0, it's exothermic, the energy went down. That's favorable. If it's endothermic, it's unfavorable. If it's endothermic, does that mean no reaction? No, it doesn't, because we also have to look at the entropy. If it's exothermic, does it mean there's a reaction? It's likely there is a reaction because energy dominates usually over entropy, and so it's likely. And so this is why I gave you the driving forces earlier, which were all energy based. But you know, we can't always be sure. And so determining the energy change is simple. We can do this quantitatively or qualitatively just by looking at the reaction. Look at the reaction using Chem 1A style, you know, stronger to weaker. stuff. Okay, but what about the entropy? You know, that's the energy change. How about delta S? What are all the ways for determining delta S? Well, one of the ways is qualitatively, you know, solid, liquid, whatever. But what we want to do is we want to do this quantitatively. Now, the way we're going to do this is this. We're going to take S final minus S initial. Now, what's the difference here? I said delta H, this is never done. We're never going to take H final minus H initial. These are called absolute enthalpies. These are called absolute entropies. Absolute entropies are determined. You could either determine these by calculation or you can determine these experimentally. These are determined. Absolute entropies are typically not determined. And if they are determined, they aren't very accurate. And the reason why we could do this with entropies and we cannot do this with enthalpies or internal energies, the same thing happens with internal energy. We never do this calculation, U final minus U initial, because we don't know what the potential energy is. And so we don't do this. But we can do it with entropies. We can do it with entropies because we know what the absolute zero of entropy is. You know what the absolute zero of entropy is? The absolute zero of entropy is given by the third law of thermodynamics. The entropy of a perfect crystal at 0 Kelvin is 0. It has 0 entropy. And so something that has 0 entropy, there's only one, there's no disorder basically, and there's only one way of arranging things. So we'll talk about this more next time, but I'm going to stop here because what I want you to do is I want you to work on the reactions, you know, that we left off last time. Do you think 30 minutes is enough to finish 3 reactions? Yeah, well, actually 10 minutes should be enough, but that's after you get some practice, right? And so it'll give you 30 minutes to finish 3 reactions. What are the 3 reactions? You guys have those? The first one I already did, so I'm giving you 30 minutes to do 2 reactions, because the first one, just make sure you copied it down correctly. I still want to check it off, but I want to see it though.